So can anyone confirm if it is visible? The screen is visible?
Yes.
Yes, sir.
Okay, thank you. So as you know, in the last class, we looked at recurrence relation, and today I am going to describe you without proof Master's theorem, which is quite useful in finding complexity of certain problems, certain algorithms. More details about this theorem you will see in your algorithm class. CS. I think probably second year or third year you will see this. So I think let me give you some brief about this master theorem and how it is connected to recurrence relations, and then we will start a new chapter on graphs. And I think some of you may already maybe familiar with this concept of graph, from any other you know courses, for example CT111, right? So you might have come across channel coding where they have described you Tanner graph or something like that, right, for decoding. So anyway, so I think we will capture basics of graph theory. So let me start. So first of all, I should tell you that there is a concept divide and conquer algorithm and recurrence relation. What is the connection? Divide and conquer algorithm and recurrence relation. So you remember we covered a binary search algorithm earlier, right? So if I want to study the complexity of that, so that means the number of comparisons in a search sequence of size n. Suppose this we denoted by f of n in binary search algorithm, right, which we have covered earlier. Binary search algorithm. Then f of n can be written as f of n by 2 plus 2. So basically, because what happens, in this algorithm, we divide the search. So in the binary search, remember, if I have a list of n objects, we divide it into half, right? Half list on one side, left side, half list on the right side, right? So bigger problem, we are dividing into smaller problems, and we are searching there, right? And then from the left half, we divide further. So this is how the binary search work, right? You take the whole you take the whole list and keep on dividing half, right, on either side. So basically, what essentially we are doing, taking a reducing a search into what is known as divide and conquer, right? We divide the problem into smaller sub problems, solve the sub problems, and then build the solution to the back. So while doing this, certainly that means the number of comparisons in search sequence of size n and to the list n by 2. There is only difference of 2 here. So what is 2 here? 2 is needed to implement the reduction. Okay, and how this is done, we can actually say that one to determine which half of list to use. Okay, and the other one to determine whether any terms of the list remain. right? So when we do the binary search, so this is the cost. So total cost of comparison in searching one object out of n, so f of n is related to f of n by 2, for the half of it plus 2, right? So this actually gives you a relationship. It's a kind of recurrence relation, okay, for this specific binary search. In general, when we are using this divide and conquer algorithm, okay, so in general, problems of size n, the problem of size n divided into a subproblem of size n by b, okay. In general, this is the thing. In this case, the relationship is f of n is equal to a times f of n by b plus some function g of n. So this function g of n is for extra operations that we do, like in the previous case in the binary search, this was 2. So this to extra operation to combine solution of subproblems, okay. So this is the general relationship when we divide a problem of size n into subproblem of size n by b. So number of comparison needed to solve the problem is related like this: f of n is equal to a times f of n by b plus g of n. Now, so this is known as divide and conquer recurrence relation. Divide and conquer recurrence relation. Now we can actually, iterate it, and to simplify, suppose n is divisible by b. So let n is equal to b raised to power k. K is a positive integer. Suppose we are looking at this kind of thing, okay. Then we can write f of n as a times f of n by b plus gn, right? And we iterate. We use again at this f of n by b, I will use this relation again, okay. So I replace f of n by b from here, so that will be a square times f of n by b square plus a times g of n by b plus g of n. So by iteration, we will get a square times f of n by b square, right, plus a times g of n by b plus g of n. This is after one iteration, right? If we again iterate, so we replace here and here, from this f of n, I replace these two things. Then what will happen? This will give us, the iteration will give us f of n is equal to a cube f of n by b cube plus a square g of n by b square plus a of g of n by b plus g of n. So if we keep on doing this iteration, finally we will get that f of n is equal to a raised to power k f of n by b raised to power k plus summation j is equal to 0 to k minus 1 a raised to power j g of n divided by b raised to power j. Right. So this is our final relationship, after iteration, Now, since n by b raised to power k is equal to 1, we have assumed, so we can do some simplification here. In this case, we can write it as f of n is equal to a raised to power k f of 1 plus summation j is equal to 0 to k minus 1 a raised to power j g of n divided by b raised to power j. Okay. So this is a final result when n is equal to b raised to power k. Okay. Now, using this relationship, we can prove the following theorem, and I'm skipping the proof right now. Okay, we can prove the following theorem. So let f be an increasing function that satisfies the recurrence relation f of n is equal to a times f of n by b plus c, where n is divisible by b, and we assume that a is greater than equal to b and b is greater than 1, and of course constant c is a positive real number. Then we can write f of n as big O of n raised to power log b base a if a is greater than 1, and this value is big O of log n if a is equal to 1. Okay. So this is a very general result. From this recurrence relation, we can prove this. The proof is given in the notes actually. So if you want, you can read it. It's a fairly easy proof. And maybe you can try to prove it yourself. That the complexity, basically the big O notation, f of n is big O of this or this. Okay. In particular, if n is equal to b raised to power k, then we write f of n is equal to c1 n raised to power log b base a plus c2, where of course c1 is f of 1 plus c divided by a minus 1, and c2 is equal to minus c divided by a minus 1. Okay, these things are possible. Of course, I am not proving the result. I leave it as an exercise because we have couple of, but I will do an example, a quick example for you. Okay, let us do an example here. So let f of n is equal to 5 times f of n by 2 plus 3, and it is given that f of 1 is equal to 7. Find f of 2 raised to power k. K is positive integer. Also estimate f of n if f is increasing function. This condition is important actually. So using this theorem that we described, using this theorem here, what we can compute, we know that a is equal to 5, b is equal to 2, and c is equal to 3, right? So if n is equal to 2 raised to power k, then we can write f of n is equal to a raised to power k f of 1 plus c divided by a minus 1. I can put those constants, minus c divided by a minus 1. Simplification will yield 5 raised to power k, 7 plus 3 by 4 minus 3 by 4 is equal to 5 raised to power k into 31 by 4 minus 3 by 4. I hope I'm doing these calculations right, but you can check. since f is an increasing function, this is given, then f of n is equal to big O of n log b base a is equal to big O of n raised to power log 5. So we can estimate this, right? In fact, another example we can do, I think this algorithm also find number of comparisons used to locate maxima or minima element in a sequence. So here, f of n is equal to 2 times f of n by 2 plus 2, and n is even here, of course. So using theorem 1, the theorem, we can write down that f of n is equal to big O of n raised to power log 2. Since b base is 2 here, this is nothing but order of n. Right. So I would like to now mention a little bit of special case here. So when c is rather than c, we have another term here, n raised to power d or something. What will happen actually? And that is known as Master's theorem. I'm going to describe now that Master's theorem. Of course, I am not proving this because, as I mentioned, you will see the proof of these facts in your algorithm class. So let f be an increasing function that satisfies the recurrence relation f of n is equal to a times f of n by b plus c times n raised to power d, right? So this extra term is there from the previous theorem, right? So this is a more general theorem. Or whenever n is equal to b raised to power k is a positive integer, a is greater than or equal to 1, and b is greater than 1, a integer greater than 1. And of course, your constants c and d are positive union 0, including 0. There may be 0 also. Positive real numbers including 0. Then f of n is equal to big O of n raised to power d if a is less than b raised to power d, big O of n raised to power d log n if a is equal to b raised to power d, and finally big O of n raised to power log b base a if a is bigger than b raised to power d. Right? So this is our master theorem, and I think you may remember this at least to find out the complexity of certain problems. So whenever we are trying to find complexity of certain problems, we try to find the recurrence relation. So when we use divide and conquer approach, we divide the bigger problem into some smaller sub problems when we apply the divide and conquer approach, and then we try to find out this kind of recurrence relation. As soon as we find this kind of recurrence relation, you can use the theorem to estimate the value. So I think I will give you one example here, especially for matrix multiplication. So you know about matrices we have covered, right? So for the matrix multiplication, if you multiply two n by n matrices, one can observe that we have the following recurrence relation: 7 times f of n by 2 plus 15 n square by 4. Here n is even. right? So applying this master theorem, f of n will be big O of n raised to power log 7. And so this is a straightforward calculation. Log 7 is, log 7 is something equivalent here 2.8. So f of n is equal to big O of, you can simplify n raised to power 2.8. So that's all for divide and conquer approach. I just gave you a brief idea about how to, uh, apply this recurrence relation method into, and the connection between divide and conquer things, right? So I think now I would like to start the new topic of
Sir,
graphs. Yes.
sir,
Yes. Your sound is not clear. Can you say it again? I can't hear you. I could hear only can you show, but what?
the sir,
Yes.
or previous.
Hello.
Hello, sir. Previous of this slide, master theorem.
Yeah, I'm showing you.
Sir, previous of this slide,
Okay, this one.
yes, sir. Okay, sir. Thank you.
Now what happens here, because the base here is B actually, right? B is 2 here, right? This B is
Okay.
2. That's why this is 1. So log 2 base 2 is 1, right? So this
Okay,
is
sir.
order of n. Okay, good. Okay, so now we would like to give you idea of graphs. Graphs are very popular subject. I mean, graphs are very important. I mean, it's very important subject. It has a wider applications. As you know, your internet itself has a structure, what is known as bow tie structure. In terms of graph when you draw. So any two computers. So each computer, if you think as a node, and you connect the two computers via the connection, if they are connected, so you get something what is known as bow tie structure of of the internet. Similarly, there are many kind of graphs, like you can make uh, you know called operations. So suppose so call graph, you call connect someone on phone, and each person who is making a call, take it as a node, and the person who is not making a call is also, you can take it as a node, and you can draw the graph, right? So the relationship is very, so when you want to find relationship between different things or objects uh, based on certain properties, what you get is known as graph, right? So basically a graph we denote it by vertex set and edges, right? So obviously, if cardinality of V is infinite, it is known as infinite graph. And if it is finite, it is known as finite graph, right? Then I think we have already covered a few basic things here, right? So set V is nothing but non-empty set of vertices, right? And E is set of edges. Okay. So then you might have come across what is known as simple graph. Simple graph, when each edge connects to different vertices and no two edges connect to same pair of vertices, right? No two edges connect to the same pair of vertices, then that is known as simple graph. Multigraph, then we have multigraph. Graphs that have multiple edges, that have multiple edges connecting the same vertex. Connecting the same vertex. Then that is known as multigraph. Okay. Loops. What are the loops actually? Loops, edges that connect a vertex to itself, edges that connect a vertex to itself. That's called loop. I mean, this is quite obvious. Directed graph if there is a direction, undirected graph if there is no direction, right? Simple directed graph with no loops and no multiple edges. Okay. So then we finally have pseudographs. A graph that may include loops and possibly multiple edges connect the same pair of vertices is known as pseudograph. Okay. So there are multiple graph models. Let me describe one or two such graphs. I think, let me show you. So if I show you here bow tie structure. Bow tie structure of the graph. You see, this is the bow tie structure of the internet. Okay, this is the paper anyway. You see that how many nodes are there. So basically, some of them are connected, some of them are disconnected components, and so on. This is the bow tie structure of the web graph. It's a very general thing. I will show you also collaboration graph. So basically, I should mention first of all what is ADOS number. So this is a very simple thing. Let me show you what is ADOS number. Okay, so basically Paul ADOS was a mathematician, and if you write, you know, Paul ADOS was a mathematician. He used to write papers. He's written many papers actually. About 800 or so, and more than 400, 500 collaborations. While you're writing a paper. So if ADOS writes a paper with someone, that person will have ADOS number 1. If that person writes a paper with someone else, that person will have ADOS number 2. Right. So basically, we can make a graph out of it by connecting edges. If somebody has written a paper with ADOS, I will connect those two people and so on. So in fact, it turns out that this graph has certain interesting properties. Anyone who has ever published any paper will have finite, ADOS number. In fact, my ADOS number is 2 actually. If you look at, and it is also known that many Nobel laureates or famous people, they have ADOS number less than 4. For example, Bill Gates has ADOS number 4, if I am not wrong. And there are many, you see, field medalists, many mathematicians, even computer scientists, they have, finite ADOS numbers. This is known as collaboration graph. Okay. So, we are uh, drawing graph by, looking at collaboration. So, known as collaboration graph. Okay. Collaboration graph. There are many, road maps that you can say, or flight map. And once you make this graph, you can actually study problems related to graphs. Now I think I will give you some idea about some graph terminology. some graph terminology. So we say that two vertices U and V in V, and I'm saying suppose the graph is undirected graph, right, are adjacent in G if U and V are endpoints of an edge, right? So basically, let me draw a picture and show you. So A, B, C, D, E, F, and then maybe G. So this is a simple graph, right? And you can see that, you know, B and C are adjacent, right? Or B and F are adjacent. Two vertices. Also, vertices are, we can write down vertex that is A, B, C, D, E, F, G. This is the vertex. How many vertices? 1, 2, 3, 4, 5, 6, 7. Right? 7 vertices are there. Okay. So these are the vertices. Now we can also define degree of vertex. For example, this vertex has degree 4. Degree of C is 4, right? What is the degree of G? Is 0, right? Degree of A is 2. Like that, you can find the degree of each, vertex. There is one, popular theorem here I would like to mention, known as handshaking theorem. So it says that if G is equal to V comma E is a graph, undirected graph actually, graph with E edges, then we have 2 times E is equal to summation U belongs to V, degree of U. So if I take in a graph, I look at the degree, and for each degree I sum. That will be 2 times the number of edges. And this is true even if multiple edges and loops are present, So how do we prove this? So the proof is very simple. Since each edge contributes to the sum of degree, right? So that's why this is 2 times this. So basically, one can, if degree is known for each, suppose degree is known for a graph and how many vertices are there, I can find how many edges using this formula, right? It's something very simple. Okay, another result that I would like to mention, theorem 2 here. An undirected graph has even number of vertices of odd degree. And the proof is simple here. Suppose V1 is set of vertices of even degree and V2 is set of vertices of odd degree in the graph, right? Then using the previous theorem, 2 times E is equal to summation U belongs to V, degree of U, right? This can be written as summation U belongs to V1, degree of U, plus summation U belongs to V2, degree of U. Right, so now we know that this left hand side is even, this side is even, and degree of U is even, right? Okay, so this whole thing will be even, right? Okay, so that means now V2 has set of vertices of odd degree, right? So this side is even, this side is even. There, this implies that even number of vertices it has even number of vertices of odd degree. This is very simple application of the handshaking theorem. Anyway, I think now I can describe another result for directed. So this was, these results were for undirected graph. Now we can describe what is known as directed graph. Means it has directions. It's a very simple thing. Let us again take an example. A, B, C, D, E. There is a direction here. There is a direction here. There is a direction here. And there is a direction here. There is a direction here. There is a direction here. Direction here. Direction here. So this is a graph, right? So A, B, C, D, E. 5 vertices. There are 5 vertices. A, B, C, D, E. And now you can see that each vertex has a direction. So I can define what is known as, in degree and out degree. So I can say that in degree of A, I will denote it by minus sign here. In degree of A is what? You can see that this is a, how many vertices are coming towards A. So one is A itself, I mean this vertex and this vertex, right? In degree is 2. Similarly, in degree of C is how much? So 1, 2, 3, right? 3. We can count what is the out degree of, say, D. So one edge is going this way out, one edge is going this way out. So there are 2 edges which are going out. So this is in degree and out degree, right? Okay, of the vertices, right? So for a directed graph, we can define like this. So once we define like this, right, now I can give you a modified result of the theorem here, previous theorem that what we were doing here now. So I think I can put another edge here, F alone. There is no connection. That is also possible, right? So A, B, C, D, E, F. So we can say that, outward degree of f is 0, right? You can also say that this is 4, out degree of b is 1, right? And in degree of f is 0. All these calculations you can do.
Sir,
Yes?
sir, suppose here and there is an undirected edge from F to E, then will it be considered a directed graph?
No. So directed graph, each edge should have a direction. Okay.
Okay, so then
Yeah.
it can be called a multigraph, right?
Yeah, I mean, I think so. Normally, directed graph, we actually always, look at when each edge has a direction. That is a simple definition, Okay.
Yes,
Okay.
okay.
So now,
Okay, sir.
yeah,
So in that case, we can what do you say, decompose that undirected edge into two directed edges, one going outward F and one coming inward F.
yeah, that is a possibility. Yeah, that you can do. Actually, so you might there are different ways we can represent the graphs. For example, adjacency matrices, incident matrix, and so on. And there, people have, there are many algebraic ways to look at the graph in that sense. So you want to see inward and outward to be separate. You may want to give a separate symbol or something like that. While making a matrix, all kind of possibilities are there. Okay. So
Yes, okay, yes, okay, sir.
so next theorem says that suppose G is equal to V comma E is a directed graph, then we have summation V belongs to V in degree of V, the same thing as summation out degree of V is equal to cardinality of, so total number of edges. Cardinality of E means total number of edges. So since each edge has initial vertex and a end vertex, right? Because directed graph means, so this is, for example, this is the initial vertex and this is the end vertex for this edge, right? Each edge has initial vertex and end vertex, right? So because of this, it's fairly straightforward to have this result, right? Now, by the way, since we are looking at graph theory, I should tell you that the graph theory started with the Konsberg river problem in Germany. And Euler solved that problem using this notion of graphs. So I would like to ask you one question. Can you make this figure without lifting your pen? Can you make this figure without lifting your pen?
No, sir. No, sir, it is not possible.
No.
Okay, so that's very good. You know that it is not possible. But I want an answer from graph theoretic point of view. Why it is not possible?
Sir, in a few time ago, you said that a number of points which have odd degree should be even, right? And if that even number is 2, then it is possible to draw a graph without lifting pen or without repeating edge. But it is other than 2, then it is not possible.
Okay. So yeah, I think you are on the right line. Yeah. So just try to write it more characteristic way. There is a result by Euler actually, in this regard. But anyway, I think that you can read more about it when you look at in detail about the graphs. And I think, as you know, Professor Rahul Muthu is an expert in graph theory. So, he will be teaching you a course on graph theory anyway. Now we can talk about some special graphs.
Sir?
Yes.
Sir, can you show the slide of theorem of directed
Yes.
graph?
This one?
Yes, sir.
Or yeah.
Okay, sir.
Okay. So basically, as I told you, the proof is because that each S has initial vertex and terminal vertex, right? So basically, you can decompose into two. So one side we are inward vertex and outward vertex, right? Is equal to total number of edges in the graph. Now some spatial graphs. I think this is very popular graph known as complete graph, right? Have you heard of complete graph? This is noted by Kn. Complete graph on n vertices. Okay, so K1 is simply single dot, K2 is this, K3 is this graph. So I think I'm just drawing pictures and I want definition from you. What is the definition of a complete graph? So there are four vertices. K5 is yes.
Sir, each and
Yes,
every
sir.
point should have equal same degree.
So simple graph that contains. So basically, first thing, it should be a simple graph, right? A complete graph should be a simple graph. There is no multiple loops and everything. And uh, so that contains exactly one edge between each pair of distinct vertices, right? There is exactly one edge. Can you see that?
Yes,
There
sir.
is one edge, exactly one edge, right? For example, in K4, you see. So this is known as complete graph. Very popular graph, quite useful in many constructions. Okay. Okay, let me describe another one. Again, I will actually draw the pictures and I will ask you to tell me the definition. Cycles. Cn n greater than or equal to 3 on n vertices and edges. So edges, of course, are 1 to 2, 2 to 3, n minus 1 to n, and n to 1. Because cycles should come back, right? This is C3, C4, C5, 2, 3, 4, 5, C6. So can you tell me what is the cycle? So cycle cycle on n vertices, and where the edges are 1 to 2, 2 to 3, 3 to 4, and so on, right? These are cycles. Got it? Next, we can talk about wheels. Wheels are denoted by Wn. So this is also vertex. This is W3, this is W4. Then we can write down W5, 1, 2, 3, 4, 5. And then there is a edge like this. W5. So wheels. So basically, wheels can be made from cycles. This is a cycle C3, right? So what we do, we add additional vertices, additional vertex to the cycle. I am adding here a vertex and then connecting the new vertex to each of the n vertices in the Cn by new edge, right? So from cycles, we can make wheels, right? So I create a here new vertex and then add everything. So like this, W3, W4, W5, right? From cycles, we can create this. By the way, another one is hypercube. Hypercubes are really very interesting. And by the way, if you look at Z2 raised to power n, this is nothing but a hypercube of dimension, you can say that n. In fact, for n is equal to 1, hypercube is 0 or 1. For n is equal to 2, there are 4 possibilities: 0, 0, 0, 1, 1, 0, 1, 1. And for n is equal to 3, this will be actual cube, we call it as q1, q2, and you can write down q3. Q3 is hypercube, right? You can say 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1. Right? This is a hypercube. All 8 points on the are vertices, right? That everything is connected. This is a hypercube, right? Hypercubes are also very important to study. There are a lot of interesting things about hypercubes. By the way, there is a interesting, result in geometry. I should ask you, and I leave it as an exercise for you. Draw seven lines and 7 points such that each line contains 3 points and through each point 3 lines are passing. Got the exercise for you? Draw 7 lines and 7 points such that each line contains 3 points and through each point 3 lines are passing. Did you understand the question? Any question here? You have to draw 7 lines and 7 points such that each line contains 3 points. See, for example, here, this line contains 2 points, right? This line contains 2 points. This line contains 2 points, right? I have to draw 7 lines and 7 points such that each line contains 3 points and to each point 3 lines are passing. Yes. Yes, somebody was asking a question. Yes, what happened? Okay, so think about it. This is your tea time question, tea time exercise. Today weather is fine here. So maybe you want to grab a cup of tea in the evening and try to solve this problem. The last, I think that's all for today. In the next class, we are going to start bipartite graph. I think you already know bipartite graph, but I'll give you some characterizations of bipartite graph, because in the decoding in the communication class you might have seen bipartite graph, right? the tenor graph, etc., right, for decoding, right? So I will give you some characterization, and some of these graph concepts are very useful, in communications, wireless communications, and many algorithms are based on graphs, because these are very, very simple thing to enumerate, right? So I think that's all. Any question at this point? Any question at this point? So I think we have 2 more lectures, and we have already posted assignment 7. So you can start doing it. I mean, you must be doing it, I hope. And the last assignment will be on, I guess, graph theory and trees, right? So I think that's all. And I think we will have exam probably on 9th of July or something. So you have enough time. And I hope you are doing your projects. If you have any question about your projects, please do not hesitate to contact me. Okay. As you know, there are 4 people can do the project together, right? So there should not be any problem. Okay, so if there are no more questions, we can stop the session.